Thank you very much. I'm really pleased to be here. I'm delighted to give this talk. I'm honored to give this talk. I'm very happy. I'm not going to say a word about big data except what I just said. In optimization for decades, people would say, well, I solve large-scale problems. That means 1,000 variables. And then someone would say, well, don't you mean 10,000? We do 100,000. And then someone would say, well, we do 1,000,000. We do 10 million. I think we're way beyond, we're several orders of magnitude beyond that now, but I'm not going to talk about it. And I have to apologize. There are hundreds, if not thousands, of references that I've omitted. I just can't cover everything. Okay, so what's the title of the talk about? Okay, it's always hard to get a good title. North Carolina, which is part of the United States, has been in the news a lot recently. The United States, for various political reasons. I'll try not to make any cheap shot political jokes about the United States. This is not quite a cheap shot joke about North Carolina, but the two topics that have been in the news about North Carolina are bathrooms, or restrooms, okay, and weddings. I, for obvious reasons, chose weddings, okay? So if you're in North Carolina today and you find the right judge, certain things are up to the judge to choose. We could celebrate the marriage of statistics and optimization with a Victorian tradition from England, okay? Which is something old, something new, something borrowed, something blue. Okay, so this is my interpretation of that for this marriage we're talking about. Something old would be to honor past contributions. Something new would be to signal that you're welcoming new ideas. Something borrowed would show that you're not exclusively saying it's only the people in our field that we're going to listen to. We'll listen to everybody. But now there's been this question about blue. Well, blue means best linear unbiased estimator. There are tons of websites about blue and statistics. There's also BLUP. There are a lot of others. So it has nothing to do with the school colors. And I thought it was particularly appropriate for this. Okay, so when I started thinking about this talk, this is sort of sticking a personal note in here. I thought I would do sort of a big sweep, talk about lots of topics. When I faced reality and started to put the talk together, I realized that was not going to be possible. There are way too many, so I'm going to talk just about two things, okay, which are related to statistics and optimization and numerical analysis, which is really what I do, okay? So the name Gauss has been mentioned several times already, so I thought it would be good when we're dividing the world up to think about Gauss, because he fits in every category. He's actually, of course, a mathematician, a statistician, a numerical analyst. He made his name as an astronomer, so that would fit in with the previous next coming SAMC workshop. And there's a great 1995 paper by Pete Stewart, which I strongly recommend, called Gauss, Statistics, and Gaussian Elimination. If you haven't read this paper, you should read this paper. This is a quote from that paper. Gauss introduced Gaussian elimination as a mathematical tool to get at the precision of least squares estimates. I don't have time to go through it, but that's what he was looking at. We tend to think of Gaussian elimination as the LU factorization when we're solving systems of linear equations. He was actually thinking about least squares estimates. Gaussian elimination was not conceived as a general numerical algorithm. It was a procedure that sprang from the interface of statistics and computation. So Gauss is a perfect example of what this workshop is about. And so I think we should think a little bit, that's what I will be talking about aspects of what we do that are connected to statistics and numerical analysis, which is called scientific computing today, especially linear algebra and optimization. Okay, so let's have the first instance. This is from both statistics and optimization, regularization. I tried to think of terms that were used in all three fields. So I'm now going to go through regularization, some history. This is the old part. An interesting aspect of this is what some people consider old is completely new to other people. You know, you could say, well, this is really well known in my field, and people say, well, actually, I've never heard of it, and the other way around. Okay, so regularization famous 1943 paper by Richard Courant, founder of the Courant Institute. It's called Variational Methods for the Solution of Problems in Equilibrium and Vibrations. Okay, it's actually online. You can read it. It's a really great paper. I'd want to point out for future reference, the word penalty does not appear, but it has a big idea. The idea is when you're trying to satisfy a hard boundary condition in partial differential equations, and you can't do it very easily. What you do instead is you pose a sequence of related problems with mild constraints, and you relax them. So you solve one problem, you relax it. You solve another one, you relax it, pushing it toward the hard constraint. And he constantly mentions quadratic functionals, in fact, the examples that he gives of how this is done. And he says rigid constraints are only idealized, limiting cases of very large restoring forces. Now, that's the paper that people always mention when they talk about penalty functions in optimization. But if you look at his paper, and by the way, with the web today, of course, you can get an old paper and you can actually scan it to see if a certain word occurs, okay? The word penalty does not occur in Courant's paper. But the way it has been interpreted is that you take the problem of minimizing a nonlinear function subject to equality constraints. You can also do it for inequalities, but we won't get into that. Now, when penalty function methods, which I will talk about, became popular, it was considered too difficult to solve problems with constraints. Too difficult to solve problems with constraints. People said we have to solve unconstrained problems. So the way this was done is that you would add a penalty function to the function you actually wanted to minimize. Okay? And then you would increase the weight on that penalty function until it became infinitely large. And that sequence of minimizers of this penalty function would converge to the solution of the original problem. And in fact, in Courant, I said he mentions quadratic functionals. So the obvious one here is the squared 2 norm of C. So you add this to the function you want to minimize. So we have a sequence of positive penalty parameters. Assuming we can do unconstrained optimization and that it's, quote, easy, we can then solve a sequence of unconstrained problems. All right? Now, you can show under relatively mild conditions that the minimizers of those penalty functions will converge to a minimizer of the constrained problem as you let the penalty parameter go to infinity. And a point that will come up later is the Hessian of, and I have written, this is a mistake, this is not of the penalty function, it's of f plus the penalty function. Its second derivative matrix is a matrix W, which is related to the Lagrangian function, and lambda is a Lagrange multiplier estimate, and then a penalty parameter J transpose J, where J is the Jacobian of the constraint functions. And if you look at this, you see a construction that's about to appear many times, which is some Hessian matrix, some matrix, and a matrix of the form penalty parameter times A transpose A, or a positive semi-definite matrix. Okay, so in this case, the penalty parameter rho becomes increasingly large. Okay, so I said 1943 was the Courant paper, and you might think, well, there must have been a flurry of activity when he proposed this idea. Actually, there wasn't. So there's a very famous book, Fiach and McCormick, Sequential Unconstrained Minimization Techniques, published in '68. And it was about the state of the art then in what they called interior point methods, which were revived in the 1980s, as we all know, and we will not discuss today, and exterior point methods, which we now call penalty methods. And so Fiach and McCormick, who were very diligent, said that basically for 10 years, no one seemed to write anything about using the Courant idea in optimization, okay? But then something happened and I couldn't find out. I spent a lot of hours on Google, but I was unable to find this. I would have to find someone who was around Not so easy now with the 1950s. And there was a software package called SUMPT, Sequential Unconstrained Minimization Technique. It was widely used through the 60s, okay? So people became worried about the quadratic penalty function, and this is another historical mystery. The fact that you had to let the penalty parameter become infinite. Of course, on a floating point machine, you can't make the penalty parameter actually become infinite, but you can make it really big. But that was inconvenient. And there was a problem about ill conditioning of the penalty Hessian. Now, I did talk to some people about this who used this code SUMPT, and I said, why were you worried about ill conditioning? And they said, it was just sort of in the air. People, let me just say, many of the people I talked to don't actually know what ill conditioning is, but they know it's bad. So they said, well, we didn't want to use it because it was the Hessian was ill-conditioned. The Hessian was ill-conditioned. And it's sort of weird. It was way before social media. So no one was sending out tweets saying, don't use penalty functions because they become ill-conditioned. But people got very worried about it and started mentioning that they were looking for alternatives because this was a problem. There were some mentions of L1 penalty functions. Zangwill proposed one in '67. Pietroskowski showed that if you minimized a penalty function with the L1 penalty term, you didn't need to make the penalty parameter become infinitely large. So there was a finite value that you could use. Of course, then there were problems of a non-differentiable penalty function, okay? So anyway, penalty function methods were around, and I'm going to put them aside for the moment and turn to another instance of regularization and optimization, namely trust region methods. Okay, this is also interesting because the term trust region methods was not used at the beginning and in fact wasn't used for quite a long time. So Levenberg, 1944, a year after Courant's paper, Levenberg published a paper in a mathematical journal and said, we're going to solve ill-conditioned nonlinear least squares problems. And we're going to take the Hessian of the ill-conditioned least squares problem, and we're going to add a positive multiple of the identity. And he talked about why you would want to do that, and he proved some theorems about it. But it was a pretty obscure mathematical journal. I found a dusty copy in the Courant library, but there was no online copy of this paper, which is somewhat unusual. All these other ones you could find it, not this one, but I did find it. But it looked as though no one had checked it out for a while, okay? So the next citation is a 1963 paper by Marquardt in the Siam Journal of Applied Math, an algorithm for least squares estimation of nonlinear parameters. It actually doesn't mention Levenberg, and as far as I could tell, people always make comments that could be sarcastic, like apparently unaware of Levenberg. I prefer to give him the benefit of the doubt and just say he probably didn't know about the Levenberg paper. And this thing increasingly comes up, by the way, as more and more papers are published. So Levenberg says he's developing a maximum neighborhood, which interpolates between its Taylor series model and steepest descent. And he clearly came out as a statistician when he published a paper called Generalized Inverses Ridge Regression, Biased Linear Estimation, and Nonlinear Estimation. But he doesn't use the word regularization. Doesn't use the word regularization, doesn't use the word penalty. Okay, so here's what a trust region method is all about. I know most of you know this, but what you're trying to do in unconstrained optimization. So remember, in the penalty case, we had to solve a sequence of unconstrained problems. So in an unconstrained method, you tend to have a model of the function you're trying to minimize, which in general will be nonlinear. The model can be either linear or quadratic. So let's take a quadratic model. That would be Newton's method if you're using the quadratic from the Taylor series. But what if there's something wrong with that? What if the quadratic model isn't a good model of unconstrained minimization? E.g., the Hessian matrix is indefinite, which means the quadratic model is unbounded below. It means you have a lot of problems. So here's the idea. You say, we have a local model. We all know Taylor series models are good, but they have this step in them that reflects how far you're going. And if you go too far, the model isn't accurate anymore. So the idea is this model is not accurate except close to where we are now. Okay, so you choose a search direction by minimize the model subject to a constraint on the size of the step you take. So you might have minimized quadratic model subject to the norm of p less than or equal to delta, where delta is some step. That's the trust region. Okay, so the idea of trust region is trust the model up to this limit, and after that you don't trust it. Okay? So you have a solution of a constrained problem, which minimizes the quadratic model subject to this norm constraint. Usually it's the 2 norm. And look, we're getting the same linear system that we had before with the Hessian plus lambda I. And you can show, even though in a trust region method, what you're adjusting is the trust region, it translates directly into this, where you have a parameter and you're making this matrix positive definite, which is sort of what was happening in the penalty function method. So you want to produce good steps to the minimizer. If the model were great, you wouldn't even have to worry about the trust region constraint because it would satisfy it, and that would be perfect. So this is the idea of a trust region method. There's hundreds, if not thousands, of papers written about it. The norm can vary. It's either the 2 norm usually or the infinity norm. If it's the infinity norm, then you have bounds on the components of a search direction. If someone wants to argue with me later about trust region methods and if they're any good, we can do that. Now, what about from the statistics side? Okay, so the ordinary least squares estimate is the minimizer of y minus x beta, norm squared. I just want to say that as an optimizer, a numerical analyst, the first time I worked with someone on a statistics problem, I said, well, the unknown x. And they said, no, x is not the unknown. X is the matrix. I said, wait, isn't it A? No, it's not A. And what is, I said, wait, what about AX equals B, AX minus B? They said, no, X beta minus Y. And in fact, Y minus X beta. So you put the right-hand side first. So this is one example of how sometimes the marriage between statistics and optimization is confusing if you don't understand that they're using different names for the same thing. You can have ridge regression. Ridge regression is an interesting term because I found at least 20 different definitions of ridge regression. I'm not going to go into the history of them, but ridge regression coefficients are the solution of a problem which is minimize a 2 norm here, and it's probably a squared 2 norm, I apologize, and a parameter lambda. It's actually called lambda, which is good because it comes up in other areas. And you minimize this. So lambda is a tuning parameter, and what is it doing? It's familiar to us from penalty functions and trust region. It's balancing between the part of the function which is this, which in this case is a 2 norm or a 2 norm squared, and something about the distance, the length of the step. It's very much like trust region methods. So lambda is called a tuning parameter. It's reflecting a balance between bias and variance. And if you interpret penalty function methods and trust region methods and this kind of method, they're kind of doing the same thing, but not completely the same thing. So there are a lot of ideas about regularization. I mean, there are hundreds. I didn't read them all. I looked at a few of them. As soon as I saw the y minus x beta, I thought, okay, this is the right kind of paper for me to look at. But there are many ideas of regularization, which have, a norm, and this is supposed to be capital X, obviously, plus a parameter times a penalty. So you can have the 2 norm, which is a standard one, and you can have other norms, just like in the penalty function case. Okay, now what about regularization? This is another interesting thing, or at least I think it's interesting. Tikhonov is the name that comes up in connection with regularization. Okay, he has a famous paper, 1943. It's on the web in English, okay? Its title is On the Stability of Inverse Problems. So you could say that was certainly a productive couple of years, wasn't it? I mean, we had Courant, we had Levenberg, and we had Tikhonov. And, you know, a lot of things were going on in the world then that weren't so conducive to mathematical research. So I feel this gives us some hope for the present. All right. Okay. Tikhonov introduced the concept of regularization in the context of integral equations. So if you look at that paper, which I have done, he doesn't use the word regularization. And he says we've got this integral equation, and then he points out that it can be ill-posed with an operator A. I liked it because there was A, okay, which is ill-posed or very ill-conditioned. So instead, what do? You minimize this. AF minus G, that's what you want to solve, and you have gamma, now it's gamma not lambda, times a smoothness penalty. Okay? In the case of Tikhonov, this is what he used. Just for your information, in case you become curious and decide to look this up, Wikipedia says Tikhonov regularization is known in statistics as ridge regression, which I found doubtful, but I leave it to one of the more expert people in the audience to say if it's right, or correct Wikipedia, please. Okay, so what about this lambda? Many course notes are on the web about regularization, and they sort of describe it, and then they'll say, how do we choose the best lambda? This is a complicated question. And then they go on and on and on about how to choose lambda and how you would do it and so on. And obviously, you have to, in a sense, do it to optimize something. You're trying to balance two things, and they have different weights. There's a technique called generalized cross-validation and a really nice paper by Golub, Heath, and Waba. And by the way, if you use R or MATLAB, you can get the way that they describe to get GCV. And there are many definitions. So I found a nice paper by Bickel and Lee that says loosely, regularization is the class of methods needed to modify maximum likelihood to give reasonable answers in unstable situations. Notice the words here that may be open to question. What's reasonable? Okay? Statisticians know, but they have different ideas. Okay? So anyway, that's about regularization. And I went on and on about this. I'm not finished with this discussion of regularization because I think penalty methods, trust region methods, Tikhonov regularization, and others are closely related, but they're different. And they illustrate the connections between statistics and optimization, but it's not usually called out explicitly. People don't say, oh, and by the way, this is a connection between statistics and optimization. The connections are getting better and better. There's a recent paper by Chaim Strabich and Zago, I don't know how to pronounce these last two names, restoring definiteness via shrinking, which is a statistical technique I will not go into, with an application to correlation matrices with a fixed block. Just came out in Science Review. So here's what this problem does. It says we have a matrix that should be positive semi-definite. We all know, anyone who does numerical computing knows this should be positive semi-definite. You compute the eigenvalues and they're not greater than or equal to 0. So they say, for example, when it's numerical data or you compute it from a distribution that you're sampling or whatever. So, and then we want to get a replacement matrix that is positive semi-definite, because sometimes it has to be. Certainly to do a lot of convex optimization, you have to have a positive semi-definite matrix. Okay, so they are going to get a replacement matrix by making a repair and adding something, sound familiar, to the matrix that doesn't have the right properties. Okay. So we form a convex linear combination of the two matrices. One of them can be indefinite. which is not typical in statistics. I mean, they're writing this paper about uses in statistics, but if you think of the penalty function use and the trust region use, it's very frequently the case that the matrix you're going to add something to is not semi-definite, okay? So they make no statistical assumptions about either of the matrices. So in fact, it's clear to me that what they're saying could be applied directly to optimization and to statistics, which is the application they have in mind. Now, for a numerical analyst to read this paper, and notice I'm not a co-author, so I have nothing to gain by telling you this is a really interesting paper, is that there are 3 methods for doing this shrinking, and they're based on ingredients that we know and love. We know and love them. Newton's method, we all love Newton's method. That's one of them. Solving a symmetric, definite, generalized eigenvalue problem. Okay, that's another problem. It's less familiar, but we know how to do it. And bisection. Bisection. How great that you can use bisection to do this. Okay, but when you do bisection, you have to check for positive definiteness. So you use the Cholesky factorization. Again, something that numerical analysts truly love. Okay, and here's the icing on the cake, maybe the wedding cake. I will come back to this later. There's software. So you need to have software for people to use these ideas. They're fairly straightforward to write down. I didn't write them down for you, but they say we have code in the NAG library from 2015, and they're making it available on GitHub in MATLAB and Python. So if you want to try those techniques to add your 2 matrices together, you can use software that's right there. Okay, now Ilse mentioned that I've worked on derivative-free optimization for several years. This is about as far from gigabytes of data as you could imagine, because these problems usually do not have that many variables, okay? But they're still important, in my opinion. So we're minimizing this function f, and we don't have any derivatives. Don't have any derivatives. We have automatic differentiation today. In theory, you can take any code, no matter how horrible, and you can run automatic differentiation, and it will give you code for the derivatives. Sadly, that's not true. It will do it for a lot, but if you have many if statements or strange constructions, which you can certainly have in most programming languages, it doesn't know how to differentiate those. Okay, so you can't assume that you have derivatives, okay? Furthermore, we tend to assume the function's very expensive, meaning it takes a lot of time. You might have to collect the data in real time. One of my favorite examples to illustrate this, because people say, well, just run it on a supercomputer. Just run it on a supercomputer. It'll go fast. Some of these techniques are used in cancer chemotherapy, where the objective function comes from a human going in, getting blood taken, and they take measurements. And then you come back in 2 weeks. Well, you can't run that on a supercomputer. You have to wait for the data. And that's an example where these techniques are used. The function's unpredictably non-nice. What we mean by that is it might have discontinuities. It might have discontinuities in the gradient. You don't know, it might have singularities. And again, with the best will in the world, sometimes you can't tell this in advance. If a physicist comes to you and says, I have this code and I don't even know what it does, we've been using it for 25 years and you have to minimize it, and you say, well, wait, what does it do? You try modern software techniques that analyze the code, they give up. They say it's too complicated. You just have to say, okay, it can be a nasty function. It may have low accuracy data. You may have to run a simulation. That's a very common instance of these things, where you, the optimizer, says, okay, what is this doing? And they'll say, actually, I don't know. Now, how can this be? Can we reform the entire scientific and engineering community and get them to write good code? I'm not prepared to do that. Maybe some of you are. Sometimes you just have to say, okay, fine. Have it your way. I'll take F, okay? So you don't want to calculate the function too many times, and I'm making this comment because certain kinds of methods that are based on nature analogies, evolutionary algorithms, genetic algorithms, swarm algorithms, simulated annealing, in my experience with them, and this is based on many, many years of experience, people say, well, it only took 10,000 function evaluations. That's okay, right? And you say, well, actually, no. To be fair, it's because they're often used in global optimization where you have to do a lot of sampling to get the answer. For people who are prepared to just take local solutions, you don't want to do that. So these methods have an interesting history. We're talking a lot about history because of the theme of this talk. So in the 50s and 60s, okay, well before I suspect anyone here was publishing papers about optimization, you could publish a paper in a good journal about an optimization method and you didn't have to have any proofs. You just said, this is a method and here are the results we got on these problems, and it would be published. And that was fine, and I'm going to mention a paper for which that was the case, okay? Then a process which has become known as mathematization, it's a mouthful, but it's known, started. Now, did the mathematicians take over? I mean, most of the mathematicians I know aren't of the takeover type. But what started happening is people said, well, where's the proof? Where are the theorems? Where are the lemmas? I don't care about these numbers. I just want to know, does it work in theory? And that started, and I again tried to find out a date. You know, someone saying, from now on, you must have convergence proofs. But I don't know when that happened, but it did happen, okay? And at that point, papers started being completely rejected. I mean, you'd apply to submit it to an optimization journal, it would be rejected. There's no theory, there's no theory, there's no theory, there's no theory. Some people thought that even having a paper where you didn't have proofs was embarrassing. And the theory was, if you don't have theory, it can't be any good, okay? So that was essential. Now, it's looser today. I think now journals are more tolerant, although I suspect you'd never get a paper published in any good optimization journal if you didn't have any theory at all. But engineering journals now and many other journals in science areas will take papers like this. Okay, so I personally think that's good. I love theory as much as the next person, but I think if you look back, and I didn't do that for this talk, but if you look back at interesting new ideas in the history of optimization, many of them would never have been published if they were submitted today. I mean, they would be laughed off the court. So this is an example of the first point, which is they were published and no one minded. The Nelder-Mead simplex method, don't confuse it with the simplex method for linear programming, has absorbed a lot of my time for a long time. Nelder and Mead, John Nelder and Roger Mead, were two UK statisticians. They were absolutely statisticians. And they worked at the National Vegetable Research Center in Wellesbourne, Warwick. I had the privilege of meeting both of them, and John Nelder told me that when this paper was published, people said, we can't possibly take this paper seriously. What's the National Vegetable Research Center? Well, apparently it doesn't exist now, but at that time, it's where a lot of statistics was used. Crops, productivity, many examples in agriculture were important, and they had a place where statisticians worked on those problems. Okay, so the Nelder-Mead method was inspired by an earlier paper by Spenley, Hext, and Himsworth called Sequential Application of Simplex Designs in Optimization and Evolutionary Operation. It was published in Technometrics, which was a good journal. And what it was about was you form a regular simplex and you move it around. Basically, you should read the paper. It's extremely interesting because they say A plant manager can use this method, and here's an example of a little form that the plant manager can fill in, you know, I guess while standing there, watching the process and writing things down. Because the simplex stays the same size, it stays the same shape, and it just moves around. And they had interesting things like you might need to evaluate the function at the same point 2 or 3 times because the configuration of the system will have changed. So it'll give a different answer. We don't tend to think of that with modern optimization, that you evaluate it at the same point, it gives a different answer. You'd be a little worried about that. Okay, so Nelder-Mead maintains a simplex. It moves it around. It doesn't retain the same shape. And if you read the abstract, it says the simplex adapts to the local landscape, elongating down long plains, changing direction on encountering a valley, and contracting in the neighborhood of a minimum. It was published in the Computer Journal in '65. The Computer Journal is the journal that published the famous Fletcher-Powell paper on quasi-Newton methods. So it was not a bad journal. But the Nelder-Mead paper has no proofs. It has some numerical examples, and it's a delight to read because both Nelder and Mead were very lively people, and they put comments in that today the editor would say, this is much too informal. You can't possibly say this. And where's lemma 1? You know, I mean, it's just a different world. It's a different world. It became, and again, this is before social media. I don't know how this news got around, but practitioners who wanted to solve optimization problems loved the Nelder-Mead method, and they didn't want to provide derivatives, okay? I know about this because I was involved in the 70s in working on the NAG library. And we had all this documentation that said, if your function is differentiable, be sure to use a method that uses derivatives. It will be much more reliable. It will be much better. Don't use this non-derivative method. Well, people just ignored that. And we tended to think it's because they didn't remember how to differentiate. I mean, actually, it's kind of a joke thing. If you have a function of 10 variables with some, I don't know, sinh and exponential and stuff, and I say to you, okay, you write down the partial derivatives, many people would just say, forget it, I don't want to do that. So they didn't want to do it. I didn't do a survey about this, but that was the theory. So people use this method all the time. And this method has been cited, I just checked a few days ago, according to Google Scholar, 24,228 times. That's a lot of cites. You can say it's because people used to cite it, but they don't cite it now. That's not true. It's cited today, and people use that methods today. Now, this perhaps is a shaky argument here, but there's a paper, 1998, that gives convergence results for the Nelder-Mead method in low dimensions, low meaning 1 and 2. I don't think very many people actually care about those results because they only apply in low dimensions and they're pretty complicated. But there are 5,138 citations of that paper, many of which are dated this year. Now, why would that be? You think, why would people want to read this paper about convergence? Here's why. The MATLAB code, fmin search, uses the Nelder-Mead method, and it gives that paper as a citation. So I've done this. You go look at those papers, you try to find out what they're doing, and they'll say, we use this MATLAB routine, cite of the paper about the convergence results. Okay, so they're using it. They're using it, even though many people would say they should not use it, okay? Now, it's very simple to grasp. I'm not going to draw the picture. It's very simple to grasp. It's very complicated to analyze. And there's a 2D counterexample. 2D counterexample for which you have a two-dimensional smooth function. Nelder-Mead fails. It never leaves the best point in the original simplex, okay? And so a lot of people in optimization have said, don't use this method. Don't use this method. Don't use this method. Use ones with derivatives. Tim Kelly, who's from NC State, said, Unlike, and he listed direct search methods with provable convergence, the Nelder-Mead algorithm can stagnate and converge to a non-optimal point. And then he proposes different strategies for detecting stagnation. A comment I want to make about stagnation is it's not a mathematically defined term. You know, if you're running a real problem and you see that the function's been evaluated 100,000 times and it's only changed the objective function by 10 to the minus 7, you might say, well, it's stagnating. But someone else could say, no, it's still changing. It's still changing. You've only done 100,000 iterations. So stagnation is not a scientifically rigorous term. In any case, given that bad stuff, why would you ever use this method? There are derivative-free methods that have convergence proofs, and they have good software. MathWorks has lots of options for derivative-free software. Okay, remember, I've worked on these Nelder-Mead methods, so you could think I'm crazy or whatever, I have no taste, I don't understand theory. But what I want to say, and this is a political statement, perhaps provocative, is convergence proofs are great, we all want them, but they're mathematical. And even if you have provable convergence for algorithms, this is true in many cases as well as optimization, methods may not work in practice very well. So even direct search methods that have convergence proofs can stagnate in practice, meaning they don't make much progress and it takes a very long time, okay? So in the 60s, there was a term called a resolution ridge. It's interesting that ridge regression is something that I mentioned earlier. So this was in the context of maximizing, and you can have a resolution valley when you're minimizing. This was described in the 60s by Wild and then Brent in 1973. And so these methods, remember I told you they were around and they were popular. People said, you have to worry about resolution ridges. So here's the definition. You have a resolution variable, some small tolerance. And x is in a resolution valley, we're calling it, if the function value is lower than x minus delta I. E is the ith coordinate vector, and less than this. Now what is this saying? The method thinks, I'm using an anthropomorphical anthropological implication that the method thinks has the smallest value. And it might think, okay, I'm done. I've gotten a better result. But in fact, it's not close to the minimizer. And that's the problem with resolution valleys and resolution ridges. But of course, you can't tell because you don't want to sample the function at all these points. And you don't have the gradient. All right. So this is a function with a resolution valley, and here it is. You'll have to take my word for it. I can give you the mathematical formulation of this, but this is a resolution valley. This function was proposed in '62 or something like that, so it's not new. And when you use a direct search method, I'm using now several MATLAB codes that have methods that have convergence proofs. Okay, I ran them. I hate to tell you for how long. Starting over here, this is where the minimizer is. And this shows the function values. It's a lot. It's a lot of function values. It does get there. Here you see it got there. It took a really long time. Now is that stagnating? Or do you say, well, it's the way it is, it got there in the end, even though it took 3,000 function evaluations. These are concepts that are outside the mathematical formulation of the problem. Let's consider Nelder-Mead. This is Nelder-Mead. Starts here, has a simplex, and there. Takes about 30 function evaluations. Now, you could look at this and say you cooked it up, it's not fair, of course it's using that. And I didn't cook it up. I could show you many, many more examples. But if you see something like this and you're a user of optimization software, you might say, well, this looks a lot better to me than the one I just saw, even though it doesn't have a convergence proof. So this is kind of an interesting situation where you bring mathematics and engineering and practicalities together. Okay? So Now, this is my final segment. I mentioned already that problems with large data sets are the main interest. When we read about what's going on at SAMC now, it mentions large data sets, large numbers of variables, and they're great problems, no doubt about it. But in my view, in my experience, and maybe it's because people know that I'm interested in non-derivative methods, I learn about other kinds of problems too, and they don't have that property. Turns out that a lot of problems in medicine have small numbers of variables, and they use MathWorks derivative-free software, okay? So here are three. You can find this out if you want by going to, well, you can use Google Scholar, or you can go to the SIAM website for the SIAM Journal on Optimization, and you can look up these papers, and then you can find out, you can get them through the magic of the modern era, and you can look through them for the word optimize. Okay, so here are three examples. One, I've got a personal anecdote to tell you. This one is about using search algorithms to try to optimize drug combinations. Well, when you think about it, in treatment of many diseases, you maybe have 4 drugs that you want to know what values should they use. It's not a big number of variables. And prediction of multidimensional drug use. So what's this personal anecdote? I had a sprained ankle. I went to urgent care. Dr. Schreck was the doctor. As we often do when we get in that situation, he said, "So what do you do?" I said, "I'm at NYU." He said, "What do you work on?" I said, "Optimization methods." And he said, "Oh, do you know the Nelder-Mead method?" I said, "What?" "What?" And he said, "Actually, I have a company and we use that method." And I said, "You're kidding me. You use a Nelder?" He said, "Yes, and it works really, really well, and we like it a lot." And he referred me to this paper and a few other papers. So I think it sort of cheered me up a little bit to think, and it certainly surprised me that he said that. And so problems like that, and I've looked at a lot of those papers. Almost all of the paper is about the medical problem. It's not about the optimization, but they use derivative-free methods. Some of them use pattern search, some of them use MAD, some of them use other ones, but they don't have large numbers of variables. They're highly nonlinear, and they don't have derivatives. Okay, so what I think we need, this is my bring statistics and optimization together, I think we need help from statistics for modeling these problems. Because if you read these papers, some of the mathematical models are extraordinarily simplistic. You know, they'll just make some, it's not like this is linear. Okay, and we know so much about statistical sampling and what we can learn and what you can learn when you have problems, and they don't include that. And I think we, meaning people that work in both areas, should be there. I think we have to decide on whether we can use statistics better. The reason I say that is many derivative-free methods depend heavily on things like the starting point, on how big you make the first step. In the MathWorks software, they might say something like, "We assume that a step of 1 in this variable will lead to a change by 1 in the objective function value." That's a pretty big assumption, and it's often not true. So what I think we should do is use statistical methods to find out more information before we start minimizing. It'll use function evaluations, but I think it will pay off. If you think about that picture with the thousands of function evaluations, you will see that having a better start and a better step would have made the method perform much better. Okay, so I'm now going to list some ideas that have been done for this. Adaptively rescaling the mesh in the method called MADS. There's a mesh, it's not as simple as you might think, and they have ways to scale it. And there's a very nice paper about how you scale the mesh adaptively in black box optimization. There's an old paper by Jane Cullum called Numerical Differentiation and Regularization. You could say, well, you don't really want to do numerical differentiation, do you? Well, no, but if you knew a good estimate of the derivative, it would tell you something you could use in the software. So it's really interesting, and she uses Tikhonov regularization. There's a paper, a more recent paper by Knowles and Renka, Methods for Numerical Differentiation of Noisy Data. Same idea. You use regularization, and you get information that would give you a good estimate of the derivative. It also tells you something about how the function behaves. It's amazing what you actually learn from the derivative. When you think about it, if you have the exact derivative, you really know a lot. Fitting response services with stochastic processes. This was from 1998, Journal of Global Optimization, where they basically say expensive black box functions. Those are the functions we're talking about. The techniques that they use are still worth it, and they're based on the paper that's listed next, Sachs, Welch, Mitchell, and Wynn, Design and Analysis of Computer Experiments. So you use design of experiments. Then there's another paper about the mesh adaptive direct search method, and then there's wonderful software from Grace Waba at Wisconsin about statistical software, regularization, and so on and so forth. So I think people in the optimization field who are doing the derivative-free methods should be thinking much more about the statistics, much more, and I hope they will. Okay, now what about other things? I mentioned automatic differentiation. Well, there's some software. There's C-Noise, Moray, and Wild, which are MATLAB scripts. They estimate the accuracy of a function, okay? And computational noise. There's a package which Larry Biegler, I think he's here, is involved in, analysis and characterization of sensitivities. I don't know how you say it, Sci-IP-opt, anyway, it's really good. There's a convex optimization modeling framework called Convex, and there's JUMP, a language for mathematical optimization. So I mention these because I had my little joke about AX minus B and Y minus X beta, but often the language in which you express a problem makes a huge difference to whether someone thinks it has anything to do with what they do. You know, you might say, oh, Y minus X beta? No, I don't do that. Then someone says, what about AX minus B? Oh yeah, okay, I do that. So, and if you think about what I said about the Courant paper and the Tikhonov paper and the other papers, it took people a while to figure out that they were talking about something relevant. Okay, so the big message, I think, my big message, is that we need to have great theory. I do think we need theory. I still am hopeful we can get theory about some of these methods, but I think we need code. I really think software is what you need. Why are so many people using these MATLAB routines and R? I have to confess, I use MATLAB and not R. Knuth has a quote that I love about his main conclusion is that software is hard and that it's much harder than writing a book or proving a theorem. I often use this, although they don't care, to people that write books and prove theorems, and I say, you should write code, you should write some software that does this, and they say, no, who cares about software? Well, the answer is if you want to maximize impact, that's what you do. You write software. And I think we're incredibly lucky that people have developed the codes in the MathWorks suites. There's statistics, learning, optimization, global optimization, and there's R that we can use to help us solve these really important problems. Okay, so I started off with the wedding. The wedding won Hopes in North Carolina, done by a judge who agreed to performance between these two different kinds of people. They lived happily ever after. Thank you.